So we talked about inflation, not so much last time. So I mentioned the horizon problem, the fact that in hot, oh, by the way, is it connected, recording? Oh, okay. So we talked about the horizon problem and the fact that if we consider lambda CDM cosmology, then we have two different points. We have not two, actually, many different points, say, on the recombination surface that have more or less the same temperature, but they have never been in causal contact with each other. And this was called the horizon puzzle. How come points that had never been in causal contact in the lambda CDM cosmology, they happen to have so similar properties? And inflation, what it does is that it's a proposal that before the period of radiation domination, there was another period with W less than -1 in such a way that these 2 points, so this was, say, the period of radiation domination, then matter domination, and lambda. But the idea was that before that, there was another period, and there was a phase transition from that previous period with W less than -1/3. In such a way that now these 2 points during that period come into causal contact. So in this way, it solves the horizon problem. Now, you can ask, so therefore the pictorial is like this. Lambda CDM cosmology just corresponds to the upper part of this, or the hot Big Bang cosmology would correspond to the upper part of this. And then the idea is to add this period in the past. Now, if you look at this picture, you see that these two different points on the two sides, indeed, they come into causal contact in the sense that the past light cones are coinciding with each other. However, as you can see, they are not exactly the same, right? The past light cone of this point is this. The past light cone of this point is this. So there will be some regions that are not, that are still different between the two past light cones. So say this region of that size. Now, since this is so as this distance is of course the same as this distance, these two lines are 45-degree parallel lines. So therefore, it corresponds to the same co-moving distance. So how does inflation exactly solve the problem? Because still the two past light cones are not exactly the same. So why should they have exactly the same or extremely close temperature to each other? After all, there could be something happening here that affects this point, and it didn't happen, but it couldn't affect that point. So still, it seems that there is a reason to be puzzled by this extreme homogeneity. So the way this is solved is that if we go long enough to the past, during this period with W less than -1/3, this co-moving distance corresponds to a physical distance which is extremely short. So let us try to compute that. Let us try to compute what is the measure of the distance, physical meaning of this distance, or compare this distance with the horizon side. So we are talking about a fixed, so let me just write a title, horizon. Problem. So I want to take this this distance delta x is effectively the horizon size, right? The biggest distance that we can observe. So this is a comoving distance. If I multiply it by the scale factor, it becomes a physical distance. It's a fixed comoving distance, but now it becomes a time-dependent physical distance. And now if I also multiply this physical distance by h of t, this combination, Hubble times the physical distance, it gives us a velocity, right? So what do I want to require? I want to require that this physical distance, as I go past to very early times, becomes an extremely short distance. Extremely short distance compared to the cosmological scale. That means that the velocity, the cosmological drift that we get by Hubble law should be much, much smaller than the speed of light, right? That's the way we can define the cosmological horizon. And since the speed of light is 1, so we want this to become less than 1. If in the past this happens, it means that this distance becomes much smaller than the size of the horizon. It's effectively as if we are talking about physics, say, on the Earth. We are talking about distances which are much shorter than the cosmological distance, and for these distances, it doesn't really matter the fact that we are living in an expanding universe. Okay, so if we achieve that, then, or more precisely, if we manage to make this physical distance between those 2 points extremely short, then it is just energetically impossible to produce perturbations that differentiate between these 2 points. Very short wavelength perturbations require very high energy, right, by the uncertainty principle. I emphasize that I'm talking about the physical distance. So we know that by the uncertainty principle, delta x and delta p has to be larger than something of order 1. Therefore, if this, we are talking about making this difference between the two past light cones extremely small, then it would be just energetically impossible to create perturbations that differentiate within this region and that region. And therefore, the difference between these two past light cones doesn't matter that much. Okay, so this is what we want this period to achieve for us, to make the past light cone of these two regions almost coincide up to a distance which is extremely short and impossible to excite. Okay, so now what does it mean that we want? Of course, another thing is that these 2 points started, at this point, they are super horizon. So it means that they are actually much longer than the horizon distance. If I do this computation at this time, this product is actually much bigger than 1. We want this product to become much less than 1 at some initial time. So let me put Ti here. Here, Ti. So at time Ti, which is this time, I want this product to be very small, while if I compute it at this later time, it is much bigger than. So therefore, since delta x is a constant, what we need is that d by dt of a times h to be larger than 1. If it is larger than 1, then as I go to the past, it becomes smaller. This means that a double dot is larger than. Wait. Sorry, not larger than 1. I need it to be larger than 0 so that it increases with time and decreases as I go to the past. So this is larger than 0, and therefore a double dot which is second derivative of A with respect to time, has to be larger than 0. Okay, let me rewrite this equation in a slightly different way. So d by dt of A times h, given that A, the scale factor, is always positive, I can write it as h squared plus h dot larger than 0. Now, how can we know that h squared is positive? So then if h dot was also positive, that would be satisfied. So that's one option. H dot larger than 0. This option is forbidden by what we call a null energy condition. So there is in general relativity, we usually put some constraints on the energy momentum tensor. These constraints are generalization of the idea that we don't have negative energies, or we don't have negative energies which are, say, unbounded below. And therefore, we can put a 0 at that minimum value, and then energies would be positive. So these energy conditions that we introduce in general relativity are generalization of that idea. One of them, which is relatively robust in the sense that we don't have any example that is violated, say UV complete quantum field theory that can violate it is null energy conditions. So there are different energy conditions. There are many of them can be violated in some circumstances. One of the most robust ones is a null energy condition. In fact, there are different versions of null energy condition. The most robust one and relatively weak one is the one in which you integrate the T mu nu along a null curve. So let me say that this is forbidden by null energy condition. Okay, let me just write what null energy condition says. It says that for any null vector k mu k nu times T mu nu should be larger than or equal to 0. In particular, if T mu nu has the form of the T mu nu of a perfect fluid, so it is parameterized by a rho and a p, then this translates into a rho plus p larger than or equal to 0. So for instance, if you consider matter or radiation, they would satisfy this by a big margin. If you consider cosmological constant, it is exactly at the border of, it saturates this bond. This also translates into saying that W should be larger than or equal -1. So if this is satisfied, then you can easily show using the Friedmann equation and the energy momentum conservation equation that h dot cannot be larger than 0. H dot will be less than or equal to 0. So these conditions would imply H dot less than or equal to 0. Now, there are models that try to solve the horizon problem using this idea, using positive H dot. In principle, you can consider effective field theories that that produce negative H dot, so violate null energy condition, but there is some evidence that these effective field theories cannot be UV completed. And on the other hand, we don't have any UV complete model that produces this. To be more precise, we can have violations of null energy condition, like Casimir energy is as an example. However, it wouldn't be enough violation that gives us what we need here. So there are models that do this, but there are some evidence that this cannot be accomplished in a complete theory. The other alternative would be that, so if we don't allow H dot to be positive, then H dot is negative, and then for this condition to be satisfied, we have the second option, which is minus H dot over H squared should be less than 1. So H dot remains negative. The universe is expanding. It continues. In the past, it was also keep expanding, but A double dot is 0. This is accelerated expansion that we call inflation. So this is the second option that we are going to talk about more. Okay. Any questions so far? So now let me draw this diagram. So I talk about this quantity, this combination that I want to make it less than 1. This product A times H is, you have seen it before, it is called a comoving Hubble parameter, curly H. We can draw this, have a diagram that shows the time dependence of this quantity, or inverse of this quantity. Why? Because this relation can be rewritten as, so if I make this definition, then what we need is that delta x times curly H at some initial time, we want this to be less than 1. Okay, so let us draw a plot of this comoving Hubble, or inverse of comoving Hubble. As a function of time, which now I parameterize it by the scale factor, so log of A. And here I put inverse of, log of inverse of comoving Hubble parameter. So this is a diagram of the logarithm of the comoving distances versus log of the scale factor. Now, the behavior of this quantity, this curly H, during a period with equation of a state given by W, it can be easily determined. So the way it behaves is that during radiation domination, it grows with the slope 1. So let's say we come here. So something like that. Or maybe that was too much. Too long radiation domination. Okay. I think that's enough. Then there is matter domination in which it grows with as the square root of a. So here would be slope 1/2, and then during lambda dominance, it will decrease with the slope -1. So this is radiation dominance, matter dominance, and lambda. So for most of, actually this lambda period is, what I drew is too long. It is, in reality, is much shorter. So most of the time, this inverse of the co-moving Hubble is growing with time. So this is what happens when W is larger than -SA. And then we want this period of inflation to the past of radiation dominance with W -SA. Again, this curve is going to decrease. Okay, something like that. So this is our period of inflation. And then this size that we determine, so what is this delta x? Let us try to remember what delta x is. So remember that this is a conformal diagram, so distances and times would be the same. Light travels at 45 degrees, so this delta x is the same as this delta tau. And we know how to compute delta tau between two different times, right? So delta x, as you can just see geometrically from this diagram, is just twice delta tau between today and the time of recombination. So we can compute it exactly or approximately. Exact computation, you can do it as an exercise. Approximately, this goes as 1/h0. Okay, so now what we want to happen is that H at the beginning of inflation, or at inflation to be long enough so that at some early time Hi divided by H0 is less than 1. In this plot, it corresponds to this. So 1/H0 will be a distance that is of order of the peak of this diagram. And then we want, and of course it's a fixed, delta x is a fixed number, right? So it's just a constant in this diagram. We want inflation to last long enough so that at some early time that I call Ti, here, no. So this time is, here we have Ti. At this time, we want this length, which is log of delta x, to become the small compared to the inverse of curly h, the co-moving Hubble parameter. This allows us to determine the length of this period of accelerated expansion that we need. So of course, the problem will not be solved if this period is very short. It has to be long enough to solve the problem. Yes?
Yes, that's horizontal line.
Uh-huh.
Just below inflation. What does it represent?
It represents log of delta x. So remember, what I want is delta x times hi to become less than 1 at some initial time ti. So I have plotted 1 over curly h, and here delta x is just a constant. Delta x is a number that we can compute. It's awarded 1 over h naught today. So this is that constant, and this is h. This is 1 over h, assuming that we have a period of accelerated expansion or inflation. When delta x becomes less than hi, it means that it is below this curve. Okay, so yes, so this allows us to compute the duration of inflation. It cannot be short enough. It has to last long enough so that it solves the problem. But you can also see from this plot that how long it should last depends on this time, the scale factor at which we have the transition between inflation and radiation dominance. This transition, remember, I called it reheating in the previous lecture. So it will be this transition between this transition. This is called reheating. And depending on when it happens or at what temperature this transition happens, then the length of inflation that we need would be different, right? So for instance, if you imagine that reheating happens at a later time, which corresponds to a lower temperature, then this line would be here, for instance. So that corresponds to a shorter period of inflation. If you imagine that it happens here, it will be even short. So how long inflation needs to last to solve the horizon problem depends on when the reheating happens. Now, I want to consider some benchmark model for reheating, assuming that this transition from the period of accelerated expansion to radiation domination happens at a temperature of order the grand unification energy. This is perhaps mostly for historical reasons. At the time when people invented inflation, grand unification was very popular. So that's why the benchmark models are. That's one reason why benchmark models are referring to grand unification scale. The second reason is that this is a scale. This is almost the highest possible energy scale when you can have inflation. And of course, that would be very exciting because then, as we see, inflation has some observational predictions that we can see there. So it would be very interesting if we can see things happening at such high energy scales, and we can learn about them using cosmological observations. So it's partly history, partly a dream. So let us therefore compute this, this ratio making that assumption. Oh, another assumption that is useful to think about. So, of course, I said that this period requires W less than minus a third, but there is a window between minus 1/3 and minus 1, which is limited, which is the limiting factor because of the null energy condition. And depending on what is exactly that W, the slope of this line is going to change. The smaller W, the closer it is to minus 1, the higher is the amplitude, the magnitude of this slope. So therefore, it solves the problem faster, more efficient. And okay, many inflation models, also observationally, we have evidence that this W cannot be too different from minus 1. So it is it is both theoretically and observationally motivated to take W to be close to -1 during inflation. Which means that, remember that if W is exactly -1, then we have just a de Sitter universe in which the Hubble expansion rate is constant, is not changing. So if W is close to -1, still the H doesn't change that much, the Hubble constant. And therefore, this Kerr H co-moving Hubble would be approximately the same as the scale factor. Okay, so therefore we approximate this. So first of all, I write this as, we can do the following. We just write this HI as HI divided by H reheating times H reheating divided by H equality times H equality divided by H naught. Now, Kerr H naught and normal H naught are the same thing because I set A to D to 1. And now, assuming that W is close to -1, I can approximate this to this first factor to be the ratio of the scale factors between this TI initial point when the observable size of the universe crosses the horizon. Oh, by the way, this thing is called horizon crossing. So I should mention. So this point when a given distance, co-moving distance, becomes equal to the inverse of the co-moving Hubble, this point is often called horizon crossing. So you will hear me saying this a lot. Okay, so that initial time where the observable universe crossed the horizon during inflation, H reheating divided by H equality. It depends, as I said, on the reheating temperature. This goes more or less as the ratio of the temperatures. There is some additional factor which has to do with the number of relativistic degrees of freedom. So if you want to write the exact formula, it is number of relativistic degrees of freedom at that time, at the time of reheating, divided by 2 to power 1/6 times T reheating divided by T equality. T equality, remember, is of order of 1 electron volt. And then H equality divided by H naught is approximately the scale factor at equality to power -1/2. We also define something called the number of E-folds during inflation. So we define A, or maybe let me do this. Let me do the following. So let's set this to 1. So that would be the moment that defining that initial time when this ratio becomes the same. And this allows us to solve for this ratio. This ratio is we define the number of equals as the log of the inverse of this ratio. So the number of equals is defined as log of a reheating divided by AI. And if we want, if we satisfy this equation, that would be given by logarithm of inverse of this expression. Okay, so now if you plug in numbers in here, using T reheating to be, or whatever T reheating that you like, you can plug in numbers and you get something which is approximately 60 times the log of, so now I'm writing the general expression for a general reheating temperature. Log of T reheating divided by 10 to the 15 giga-electron volt. So if you set T reheating to be a God temperature, which is about 10 to the 15 giga-electron volt, then you say get number of equals equals to 60. Oh, G star is the number of relativistic degrees of freedom. So when you have, the idea is that you have a transition from inflation to radiation domination at that high temperature. Now, the energy density in radiation is proportional to T to the fourth, but also depends on the number of relativistic degrees of freedom that you have. G star is that, the number of relativistic degrees of freedom at the time of reheating. Here you see divided by 2. 2 is the number of relativistic degrees of freedom at equality. It's actually, there are also neutrinos like this. 2 is just the part which has to do with the part that is, so it's actually the number of relativistic degrees of freedom that are in thermal equilibrium with photons. So at reheating, it will be just photons. You say in Einstein equation? I'm not sure. Which, are you talking about the Newton's constant? No. Okay. Yes? Yes.
Why do you set it the ratio HI by H dot equal to 1?
Oh. Yeah, this is very important because no, a little bit lower. So, because what do I want to achieve? What I want to achieve is that there is some co-moving distance that I call delta x. It's say the distance between the two sides of the co-moving distance between the 2 points on the 2 sides of the recombination surface that I'm seeing. Right? The distance, co-moving distance between those was delta x. That delta x, right, so here. This is delta x. That delta x, you can compute it, given what we know about the composition of the universe. And this is something of order 1 over h now. Now, what do I want to achieve? What I want to achieve is that I want to have long enough accelerated expansion so that at some early time, this co-moving distance becomes a physical distance which is much, much shorter than the horizon size. So the condition for that was this, right? Delta x times curly h, or delta h times a times normal h to be less than 1. So I just plugged 1 over h naught in this equation. This being less than 1 means that I'm here. This being equal to 1 is this intersection between the two. So I'm trying to solve for this initial time that I need. Of course, inflation could last much longer towards the past, but the part that is actually accessible to us, we see, would be from this time ti after 1. We need at least this amount of inflation to solve the puzzle. Other questions? Yes? Sorry, say again. These blue lines? No, these are just some, I was just trying to say that you can have different scenarios in which reheating temperature is different. So I was just trying to demonstrate that if there is a lower reheating temperature, so this one has this is a lower reheating temperature than this, because transition to radiation dominance is happening later. And this is a lower reheating temperature than this. I was just trying to demonstrate pictorially that if you have a lower reheating temperature, you will need shorter period of inflation to solve the horizon problem, right? Because then this, you can compute this distance. This distance is shorter than this distance. What is this? Some is the square root of this length. So anyway, so yeah, that was it. Okay. So we need about 60 E-folds of inflation. It's called E-fold because we are taking a log in natural basis of the scale factor. We need 60 E-folds of inflation to solve the horizon problem. Approximately 60 E-folds. It depends on the reheating temperature. So now we want to write some model that realizes this. So can we have a simple realization of this scenario? And the answer is yes. Simplest realization is to just use a scalar field. So we want so I'm using a scalar field phi. So something to notice is that if I just have a scalar field with a potential, let me write it. Okay, I write the whole thing. Minus 1 over 2 d phi squared minus v of phi. So imagine this is scalar field, and suppose the potential for this looks like this. We have v of phi that is like this. And our scalar field is just trapped here at the bottom of this potential. So phi dot is equal to 0. Naively, this achieves what we want. Why? Because if we compute the energy momentum tensor of this scalar field, or that means don't compute the energy momentum tensor, just write rho and energy density and pressure, assuming that there is no, okay, for now, let's actually forget about this. Later we come to it. So if I compute rho for this scalar field, this is, of course, for general potential. I'm sure you have seen this, at least in Mustafa's lecture, if nowhere else. P is equal to phi dot squared over 2 minus V. So now, if you look at this, this is assuming, here I assume that the gradients are 0. So I'm considering a homogeneous. The scalar field, of course, homogeneity is what is the requirement of having FLRW solution. So it's like we are talking about the background, which is homogeneous. So here, you can easily see that if phi dot is equal to 0, then we will be having P is exactly equal to minus rho. So W equals minus 1. Of course, this is not surprising. This scenario corresponds to a scalar field sitting at the bottom of its potential, and the minimum of the potential can always be shifted by adding a constant. It's degenerate with a cosmological constant. So the scalar field sitting at its minimum is equivalent to just having a cosmological constant. This was actually the first, one of the first, I'm not sure if it was one of the first proposals for having inflation by Alan Guth. It's called old inflation. Now, or maybe not exactly this, but we will arrive to that. So this achieves one of the goals, which is getting accelerated expansion, because it gives W minus 1. But actually, this is not a good scenario. Why? Because, of course, we want inflation to end and have a transition into radiation domination. While in this picture, there won't be any transition. We will just have accelerated expansion of the Ceter universe. So this is not good, but a realistic potential, or you can imagine that the true potential for this scalar field is not like that. Perhaps the true potential is, let me use a different color. The true potential perhaps has other minima. So instead of being like this, there is another minimum which goes very close to 0. This is not exactly 0, but you cannot see the difference because it's very small. Or perhaps there are even, we have even not just one scalar field, but there is a lot of scalar field. There is a landscape with a lot of minima, other directions. And then there will be a very complicated potential for these multiple scalar fields. But now, for now, let us just focus on one of them. If the potential is like this, then at some point there can be a tunneling from this minimum, which is called a false minimum, to this other minimum, which in this case is a true minimum of the potential. This tunneling is called Coleman-DeLuca tunneling. And now you can see that you can have a period of inflation here, which ends by tunneling into a new minimum, which now has much smaller cosmological constant, and then in principle you could imagine a transition to radiation dominance after this tunneling. This was actually the early proposal by Alan Guth called old inflation. However, this is not phenomenologically acceptable. Why? Because there are several reasons, but the simplest reason is that the Coleman-DeLucia bubble creates a universe which has curvature, it is negatively curved. And as a result, right after the end of inflation, you will have omega k of order 1. Now you can see that it's very an easy thing you have probably seen, or if you didn't see, do it as an exercise. That yes, it is Coleman and DeLucia. Oh, I'm not sure if there is 1C or 2C. Maybe 2C. This you should check. Yes. So we have large curvature after the end of this after this tunneling. And this is a large omega k right after the end of inflation, or at the beginning of this radiation-dominated era. Now you can see that actually omega k grows with time compared to other components like radiation and matter, right? Because it is equivalent to W equal to -1/3. As a result, if you start from omega curvature of order 1, today it will be much bigger, or it will be much more important than radiation and matter. It will be less important than cosmological constant, but more important than radiation and matter. So this is, of course, not what we see. We see that we live in a universe that is almost flat. And as a result, this proposal doesn't work. It's not phenomenologically viable, but we can modify it in a simple way to make it viable. So instead of having, maybe this is. Instead of having a scalar field that is, yes? What is what? Oh, I'm just considering the background solution. So I want to have just a homogeneous and isotropic cosmology. It's homogeneity. Exactly. Yes, it's just a requirement of having a FLRW cosmology. Oh, no, here I'm saying that, so let me actually write that. So this is coming from the requirement that I'm looking for FLRW cosmology. This is an assumption. I'm saying if phi dot is 0, then P is going to be equal to -ρ. Then phi dot is going to be 0 if it is trapped in a minimum, right? If it's not if the scalar field is not trapped in a minimum, if it is somewhere else, then maybe at a moment it can be 0, but then it starts moving or rolling down. So that would, at one moment, it would give you W equals -1, but then it starts deviating. But if I want to have W equals -1 for a long period, as I say, I need a long period of inflation. If I want it to be close to exactly -1 for a long period, I should put this scale fee in a minimum so that it sits there. However, this doesn't work, so I don't want to let it sit there. Actually, it should, the way to make it work is to consider a potential, or maybe instead of saying that the way to make it work, I should say another possibility. That will work is to have what is called a slow roll solution. So if you consider the potential that is not it's not exactly flat, or field is not exactly trapped in a minimum, but it is approximately flat. So say imagine you have a potential that looks like this, and our scalar field is here. So now it is slowly rolling down the potential. However, we can have a situation in which so this is a slow roll, inflation. We can have a situation in which it is slowly rolling, so phi dot is not 0, but still, if it is much smaller than the potential, W will be close to -1. So remember, we don't need W exactly -1. We just need to be close to -1, or less than -1/3, strictly speaking. So what we want is phi dot squared to be much less than V of phi, and then the slow roll solution is defined by imposing also another condition. It turns out that it is it has an important consequence to have phi double dot to be also much less than h times phi dot in absolute values. Under these two conditions, then the equations for the background evolution will simplify. So the Friedmann equation will be, so look at here, the energy density is phi dot squared plus V of phi, but if phi dot squared is much less than V, the energy density, which sits on the right-hand side of the Friedmann equation, would be dominated by V of phi. So here I just write V of phi divided by 3 times m Planck square. So now you can you can see figure out what is the definition of the Planck mass from this equation. And then in the equation of motion for the field, I have phi double dot plus 3h phi dot plus v prime of phi equals to 0. And in this equation, the first term would be much smaller than the second term. And therefore, phi dot will be approximately minus v prime divided by 3h. Now, under these assumptions, I obtain this solution, which is called the slow roll solution. Now you can see what are the conditions on the potential that such that this solution is consistent with the assumption. So we can a posteriori verify that when that this system is consistent. And that translates into the two requirements. So here, remember, we had two conditions, condition 1 and 2. These two conditions translate into, let me just write it here so that you can see. So 1 and 2 lead to two conditions on the potential, which is the following. So epsilon much less than 1 and eta, absolute value of eta much less than 1, where epsilon and eta are defined as follows. Epsilon is defined as m Planck squared v prime squared divided by twice v squared, and eta is defined as m Planck squared v double prime divided by v. So using these solutions, this solution and this solution, if we plug it back in here, we will get those conditions. Okay, so now the important point is that when these conditions are satisfied, this Laurent solution that I define here is an attractor solution. What does it mean? It means that if you consider the phase space of this model, you have, say, a scalar field is satisfied. Well, for now, there is no gradient, so it's really 1 degree of freedom. This satisfies the second order differential equation. So in its phases, you at least have phi and phi dot as the data, initial data for its evolution. In this phase space, if these conditions are satisfied, there is an attractor line in which phi dot is determined by phi. So you can see it here. Given a phi, you know v prime of phi, and given a phi, you know h, and therefore you know h, and you know phi dot. So there is a line in the phase space, and phi dot is determined by phi. And this is an attractor. You can show it by looking at this equation. That it's an attractor solution, meaning that if you start from an initial condition away from this line, it will be quickly, within a time scale of order of h, it will be absorbed. It will it will approach this attractor line. And once you are on this attractor line, then phi acts like a clock, because phi just tells you where on the attractor you are, and then you just follow this attractor. Yeah. So, yes? These are the conditions. These are two conditions on the potential that guarantee the existence of the attractor.
Yes, but they depend not only on the potential, but also the other condition, right?
No, they do not depend on how. They only depend on the potential and the Planck mass. Okay, so the fact that this is an attractor is very important. You see later. It becomes related to the fact that perturbations of this scalar field will produce adiabatic fluctuations that Julian talked about in the CMB course. Okay, so there is not much time left. But however, I think it's enough that I just tell you about reheating. So the rolling scalar field, this inflation ends when these conditions are no longer satisfied. So for instance, in this example, this scalar field rose slowly, but at some point it arrives to the bottom of the potential where these conditions are not necessarily satisfied anymore. See here, V goes to 0, so epsilon cannot be small anymore. Similarly, eta, they are divided by V. So you arrive here, and then the conditions are no longer satisfied. Your equation of state is going to change. And for instance, one possibility is that you can, at the bottom of that potential, you can have just a, so consider generic potential. Near the minimum, it looks like a quadratic term, just by Taylor expansion. So it is defined by some near in this region. You can, in this region, you can approximate it by V of phi being given by m squared phi squared over 2. And then if we have, going back to that equation of motion for the scalar field, that equation for this particular potential becomes, looks like this. This is something that Mustafa talked about. So this is, let me draw the axis. So this is V of phi. If we are in a situation when m squared is much bigger than the Hubble squared, then we will be in an opposite regime as what I talked about before. So instead of neglecting this term, now this is the term that is negligible. And then the solutions that we get for phi will be phi of t is given by, approximately given by a constant divided by the scale factor to power 3/2 times sine m times t minus some integration constant. Now, if we compute the energy density for this configuration in this model, for this solution, you will find that rho of t will be given by, it will be proportional to 1 over AQ. Yes?
What does delta represent?
Delta? What delta?
V
Yeah.
A over
A over A of t.
delta.
No, there is not a, is this sign? This, right? It's just sine. Okay, so yes, so what happens is that this, after inflaton rolls to the bottom, it is gonna flux because of this sign, it's gonna oscillate at the bottom of this potential, and its energy density decays as 1 over AQ. So the equation of the state now, instead of being close to -1, becomes close to 0. It's like having matter. What is the interpretation of that? Interpretation is to have a collection of massive inflaton particles that have very small momentum, and then it's enough to have a coupling between this phi field and the standard model field, say lambda times phi squared times Higgs squared. It's enough to have a small coupling between this phi field and the standard model to transfer efficiently this energy in the inflaton into a standard model, and then standard model is interacting, so that energy will thermalize and you will get radiation domination. So that would be, so this is a general picture to have in mind. The slow roll solution upon the potential where the slow roll conditions are satisfied, and then the slow roll conditions are not satisfied anymore, and then you transfer energy from inflaton into a standard model because of some kind of coupling that we have in the model. Now later, tomorrow, we'll talk more about, I'll talk a bit more about a particular potential that I really like, but it's ruled out, and then we continue. Thank you. Questions?
About the last thing that you were talking about, the standard model, will you tell us about the symmetry of the possible symmetries that must or should have this scalar field?
Symmetry is that what?
That should have this scalar field.
Inflaton, the phi field. Yes. The only symmetry, not exact, there is an approximate symmetry that you need to have for this scalar field, because in a sense we want the potential for this scalar field to be flat enough in some sense. That flat enough is quantified with these conditions, right? So these are the derivative of the potential being in some sense small in Planck units. So when you have, of course, an exactly flat potential would mean that actually nothing depends on this position of the scalar field, which would mean that you have a shift symmetry for this scalar field. Shift symmetry means symmetry under phi going to phi plus a constant. Obviously, this is not an exact symmetry. This potential depends on phi. So there is, it's broken, but we want it to be softly broken. Now you can ask if the coupling between phi and the Higgs that I wrote is compatible with this symmetry. Compatibility would mean that that lambda parameter, the coupling constant, should be sufficiently small, for instance. Or you could ask if this flatness, this symmetry is compatible with some embedding in a full quantum gravity. Are there some UV effects that can spoil this? This is really the main symmetry that needs to be protected. Approximate symmetry that needs to be preserved as an approximate symmetry. I was planning to talk about it today, but obviously I didn't have time. So maybe later.
Yeah, so the heating is the process in which the inflaton decays into standard model particles.
Yeah? Reheating. Yeah, reheating is just, it's a general name. Reheating is really the transition between inflation and a radiation-dominated phase. Now, this can happen in different stages. For instance, you can have a phase in which energy goes from inflaton into one particle without becoming like a thermal radiation, and then a secondary phase in which that energy density thermalizes. So sometimes people, for instance, talk about preheating. Preheating would be the transfer of energy. Reheating is a more general term which corresponds to the full process of going from one phase to the other, inflation to radiation domination. Yes?
Potential must always be dependent on V squared, or we can choose another type of dependence on potential.
No, like the one that I drew is not symmetric on the phi 2 minus phi. No, no, I don't think it has to be dependent on phi square. Say again? I'm not sure if I understand the question. Yeah. So e to the phi. Okay, then what? What's the question? Oh, are there implications? Well, any potential that, yeah, I'm still not sure. Maybe this is something that we should discuss more in this. Whatever potential that you choose doesn't have to be a function of phi squared. Like exponential potential, you yeah, I think it can satisfy this condition. Yeah, any potential, as long as it satisfies these conditions, it can have inflation. But maybe I didn't understand the question, we can discuss. Yes? Yeah? The first picture, you mean this one? Yeah. Yes? Yeah. So the first phase, the false vacuum, could have some temperature, non-zero temperature, for example. Well, if it has, it will decay to zero super quickly. Okay, but so the reheating starts from zero temperature? Yeah, effectively. I mean, it's not exactly zero because in a curved space-time. So as I mentioned in the previous lecture, you have some de Sitter fluctuations. It's not, you cannot really call it zero temperature, but it's extremely small compared to what we need for reheating, right? The reheating temperature is much, much higher than the Hubble parameter. No, it's not. Just consider a bomb. It's cold and it exploded, it becomes hot. Well, this is exactly what you want from the inflation, but it's not so counterintuitive. It's like I don't know, a bomb is one example. Another example, just imagine a particle rolling on a cliff. So it has a lot of potential energy, but then it falls and then it oscillates and produces a lot of heat. You are converting potential energy into other kinetic energy. Yes? Oh, I think there is a signal that I have to end, so maybe we discuss it. Okay. I haven't quantized yet, except this part was quantum. This tunneling, but of course it didn't work, so no, in this picture, so far everything was classical. So we reconvene at 4, right? Okay. Thank you.